Synthetic division is a shortcut method for dividing polynomials when we have a linear divisor. That means that the thing we're dividing by has a degree of 1, a highest exponent of 1. So an example of one we can do with synthetic division is the problem that is here, since the divisor, the denominator of the fraction, has a degree of 1. Now, the first thing you're going to notice here with synthetic division is that our division box is flipped upside down to what we're used to seeing with regular or long division. To set up our synthetic division, let's take whatever our divisor is, set that equal to 0, and solve it. The solution that you get will be the number that goes on the outside of your division box. On the inside, you're going to list all of the coefficients from the numerator that you see. Just the coefficients. You don't need the variables to be attached anymore. When we start this problem listing the coefficients on the inside, it is a 1x cubed that we start off with. So the first slot inside our box is going to be a 1 for that 1x cubed. Now, before I go any further, I need to be sure that every power of x is represented in this problem. You started off with an x cubed. There is an x squared, there is an x, and there is a constant value, so there are no missing terms. If terms are missing, you have to put 0 in your box to hold the place of anybody that is missing. This one wasn't missing anything, so we can just keep going listing our coefficients. 1x cubed started us. Here is a negative 2x squared. Make sure that you see that the sign is part of it, and it's a negative 2 that we've listed. Then we had a 3x, and back on the back a negative 4. The sign was part of that again. Here is our synthetic division box set up for us to complete the problem. When you begin synthetic division, whatever number you've got here, regardless of what it is, that number comes all the way down below our division line. Now, as we begin the process of our dividing, what we're actually going to do is take the numbers below that line and multiply with our divisor. Whatever numbers are below the line will get multiplied with the 2 that is out in front. That will determine what goes in the next slot for our division box. So here, 2 times 1 made 2, and that 2 goes in the next slot in our division box. When we've completed that multiplication diagonally, now let's add vertically. Straight up and down, negative 2 plus 2 made 0. Anytime that you get a number below the line, what you do with that number is then take it and multiply with what's out front to determine the next slot in your division box. So here, 0 times 2 made 0. Once we have that next number, let's add vertically. 3 plus 0 made 3. Diagonally multiply, 3 times 2 made 6. And vertically, let's add, negative 4 plus 6 gave me 2. The number at the very back is the remainder as if we had divided this with long division. So the 2 at the back is the remainder when you divide the polynomial on top by the polynomial on the bottom. Now, the stuff that is left here underneath our line, that's the coefficients for our quotient. The quotient is the answer to the division problem. Remember that we've pulled one factor out, so the answer here has to be a degree lower than the numerator started off. The numerator started with a degree of 3, so our answer is going to have a degree of 2. This then will be the coefficient of the square term. Here is the coefficient of the x, and there is the constant value. So as I write my answer, it would be 1x squared, or just x squared. Do I need to say 0x? 0 times anything, it just goes away, so we don't need an x term. And then plus 3 for the constant value. Now I still need to account for my remainder. To do that, let's always put a plus sign here next, and let's put our remainder 2 over the thing we were dividing by, which was x minus 2. So here is the solution when we divide the stuff on top by the stuff on bottom. Now, that's how synthetic division works, but why would you want to use it? First thing, it's much faster than trying to do long division once you get the hang of it. But a second thing that is very nice about synthetic division is what is called the remainder theorem. Keep in mind, we just divided by 2, and we ended up with a remainder that was 2, coincidentally 2. It didn't have anything to do with what we were dividing by. But if we were to take the numerator of the fraction that we were just working, and let's call that f of x. Here is that numerator written as f of x. If we now try to do some substituting to evaluate at f of 2, remember that 2 was the thing we just divided by. Take the 2 and let's put it in for all of the x's that we see, and then let's do the arithmetic that results. So here when I do this, 2 if you cube it made 8. 2 squared is 4. 4 times negative 2 is negative 8. 3 times 2 made 6. And then back on the back was negative 4. Those 8's are going to add out. So I end up here with 6 minus 4. 6 minus 4 is just 2. This 2 is the same as the remainder that we had a minute ago. So the number that we divided by, that's as if it was an x that we've substituted in for all of these things. The remainder that we got is the value that pops out as if we had substituted 2 in for all of the x's. What we're going to see later on is the number you divide by is an x value, and the remainder that you get, or the number that you got when you evaluated it, is a y value. So this lets us form an ordered pair that is part of this function. That's called the remainder theorem. Now let's try one that's a little bit harder because it's missing some terms. Here, notice that I've already got my box started to be set up. We took the divisor on the bottom and set it equal to 0 and solve, and that really gives me just the opposite of the number that's here. That's what goes on the outside. Opposite of positive 3 is negative 3. We had a 1x to the 4th that started us off. Now, do I have here an x cubed term? I don't. Since that term's missing, I need 0 to hold the place of that x cubed term. I do have an x squared. The coefficient here is a negative 1. We're missing an x, and then back on the back is a constant value of 5. It is very, very important that you see that we've got those zeros holding the places of the things that are missing. Without those zeros there, you won't be able to get to the right quotient. So anytime a term is missing, put 0 in to hold its place. Now, just like before, let's bring down the first number all the way below the line. Diagonally, I'm going to multiply. Vertically, I'm going to add. 1 times negative 3 made negative 3. Add them up, and you get negative 3. Negative 3 times negative 3 makes positive 9. Add them up, you get an 8. 8 times negative 3 made negative 24. Add them up, you have negative 24. Diagonally, let's multiply. Negative 24 times negative 3, that makes positive 72. And when we add them together, it looks like 77 is going to be our remainder. Now, the quotient that we've got, remember this is 1 degree lower from where we started. So if this is an x to the 4th, 1 degree lower, this says 1x cubed minus 3x squared plus 8x minus 24. Now let's account for our remainder by saying plus 77 over x plus 3. The remainder over your divisor here was our solution when we divided. Now, remember we talked a minute ago about the remainder theorem. We said that whatever we divided by, that's as if it was an x that we substituted, and the remainder that we get out, that is a y, as if we had evaluated the function at -3. Let's see if that's going to hold true for this one. Here, I've taken the numerator and called it f of x. The number we divided by was -3. So let's take -3 and put it in for each of the x's that we see. -3 to the 4th, and here minus -3 squared and plus 5. Now -3 to the 4th, that's an even number of negative factors, so it's going to end up being a positive number, and 3 to the 4th is 81. Here, -3 when you square it made positive 9, but opposite of that is -9, and then let's bring down the plus 5 that's at the back. 81 minus 9 made 72, and 72 plus 5 made 77, just like we thought it would. So this again gives me an ordered pair. -3, the number we divided by, is an x value. 77, the number that was our remainder, is a y value. One more example so you don't get tripped up by some of the wording of a question. Here is x plus 6 a factor of x cubed plus 9x squared plus 14x minus 24. For something to be a factor, that means that it is evenly divisible by the thing we are dividing by, our divisor. That means at the end of your dividing, you need to get 0 for the remainder if it is truly going to be a factor. That's what we're hoping to see to be able to answer this with a yes. Now, let's set up our division. On the outside of the box, the thing we are dividing by is x plus 6. So opposite of that plus 6, it's a -6 that needs to be on the outside of our division box. On the inside, let's list all of the coefficients, making certain that no terms are missing. We have a 1x cubed, a 9x squared, a 14x, and a minus 24, and no terms were missing. 3, 2, 1, and constant, so nothing was missing. The first number comes all the way down regardless of what it is. Once we have a number below the line, we take that number and diagonally multiply to fill the next spot in our box. 1 times -6 is -6. 9 minus 6 gave me 3 when we vertically add these things up. Diagonally, let's multiply. 3 times -6 made -18. And if we add these things together, now I'll have -4 adding vertically. -4 times -6 made positive 24. When we add them up, did we get 0 as our remainder? We did. Now 0 as a remainder is going to make us very, very happy soon, because that means not only is it true that x plus 6 is a factor of this polynomial, we could answer this with a yes, but more importantly, we've just found a very special kind of a point. Our remainder theorem told us who we divide by is an x. The remainder that we get is a y, so we just found the point -6, 0. Now, anytime your y value is 0, what you found here is what is called an x-intercept. -6, 0 is an x-intercept of this polynomial. That would help us to be able to draw the picture soon.